16 billion miles from here in the dark between stars, a dying machine is listening to something. I've been hearing it for 9 years. It has never stopped. And nobody on Earth can tell you what is making the sound. Not a burst, not a glitch, not a signal from anyone. Something stranger than that. And something that, in a few months, we may lose the ability to hear forever. Here's why this matters to you, sitting where you are right now. That machine is Voyager 1. It is the only instrument our species has ever placed inside interstellar space. Not near it, not looking at it through a telescope, inside it. Everything we think we know about what lies beyond our solar system was built from the outside looking out. Models, mathematics, theory. Voyager 1 is the one and only fact check we have ever run on all of it, and the fact check is failing. Because what it is measuring out there does not match what the model said should be there. Not slightly, fundamentally. By the end of this video, you will understand exactly what that continuous emission is, why researchers still cannot agree on its cause, what it implies about the shield that has protected every living thing on this planet for 4 billion years, and why NASA has already circled a date on the calendar down to the second that our civilization has never reached before. Stay with me. There's a moment about 11 minutes from now where this story stops being about physics and starts being about survival. Before we go further, if you want the version of these stories that goes past the headline and into what the data actually says, subscribe. This channel is where that version drops first. But to understand what Voyager 1 is hearing, we have to go back. All the way back. September 5th, 1977. Cape Canaveral, Florida. A Titan Centaur rocket lifts a spacecraft off the pad. The spacecraft weighs about 1,800 pounds. It is roughly the size of a compact car, dominated by a 12-foot dish antenna that will spend the rest of its existence pointed at one specific dot in the sky. Us. It is, in the most literal physical sense, the edge of home. In August 2012, 35 years after launch, Voyager 1 crossed it. How did they know? Because the readings flipped. The particles streaming out from our sun dropped off sharply, cosmic rays from the wider galaxy jumped up, and the density of the plasma around the spacecraft rose by a factor of roughly 40. 40 times denser. That is not a boundary you drift across gently. That is a wall. Voyager 1 became the first object built by human hands to exist in interstellar space. And then, and this is the part that still doesn't feel real, it kept transmitting. But here is where the story starts refusing to behave. Because for decades before Voyager got there, physicists had built careful, peer-reviewed, mathematically rigorous models of what interstellar space should be like. Those models broadly agreed. The space between stars should be thin, cold, sparse, quiet. A smooth, low-energy background, a kind of cosmic waiting room. Voyager 1 walked into the waiting room and found the weather. In 2017, the plasma wave subsystem on board, an instrument that essentially listens to the vibrations of charged particles the way a microphone listens to air, began registering something new, a narrow band emission, faint, persistent, continuous, not a spike, not an event, not a burst that came and went, a steady ongoing signature in the plasma itself. Researchers analyzing that data, published in the journal Nature Astronomy, described something the field had never had before. Not a snapshot of interstellar plasma, but a continuous readout of it. Before this, measuring the density of interstellar plasma required luck. You had to wait for the sun to throw a massive eruption outward, wait months or years for that shock wave to travel all the way to the heliopause, and then watch it ring the interstellar medium like a struck bell, scattered, occasional, years apart. It was like trying to understand the climate of an entire continent by checking one thermometer in one city once a year. The persistent emission changed that. Suddenly there was a running feed, day after day, year after year, a moving portrait of the space between stars measured from inside it. And the portrait showed something the models had gotten wrong. Interstellar space is not smooth. It is not uniform. It is not quiet. It is turbulent. It has structure. Its scales ranging from small enough to measure across the width of the spacecraft up to structures stretching across hundreds of millions of miles. It has texture. It has, for a lack of a better word, weather. The space between stars is not empty. It is full, it is moving, and it has a personality that we are only now, for the first time in the, but that's not even the strangest part. Because there are two competing explanations for what that emission actually is. And after 9 years, the scientific community still cannot say which one is correct. The first possibility is thermally excited plasma oscillation. In plain language, the plasma is naturally jittering because of its own heat, and Voyager is picking up the vibration. That would be a significant find, but it fits inside the physics we already have. The furniture stays where it is. The second possibility is something called quasi-thermal noise, a different mechanism, encoding information about density and temperature in a subtly different way. And this is where it gets uncomfortable. Because if the second explanation is the right one, then existing models of the interstellar medium, the models that underpin how we estimate the density, the temperature, and the behavior of the entire space between stars, need substantial revision. Let me be precise here, because I don't want to sell you something the data doesn't support. No one has claimed this is artificial, and no one is suggesting it's a message. It is a physical process. Nobody is arguing about that. What they cannot agree on is which physical process. And that disagreement is no footnote. It determines whether our picture of the galaxy's basic structure is roughly right or meaningfully wrong. So how do you settle it? You need more data, either from Voyager 1 itself, which is producing less every single year, or from a new spacecraft, purpose-built, with instruments designed specifically to answer this question. Here's the problem. No such mission currently exists. None is funded. And even if one were approved, funded, built, and launched today, it would not reach the heliopause for roughly a quarter of a century. Hold that thought. Because it becomes the most important sentence in this video in about 8 minutes, and then things got worse. Because the emission is only half of what Voyager found there. The other half is the boundary itself, and the boundary is nothing like what we drew on the diagrams. Every textbook illustration you have ever seen of the heliopause shows a soft gradient, solar wind thinning out gently on the inside, interstellar medium fading in gently on the outside, two environments blending like a river meeting the sea. That is not what is there. Measurements from the Voyager probes indicate that in the region near the boundary, particle temperatures reach the order of tens of thousands of degrees. Figures on the scale of 30 to 50,000 degrees have been reported from that data. At the outer edge of our own solar system, in the region that was supposed to be a cold, empty transition space, some researchers have used the phrase wall of fire to describe it, and it has understandably escaped into headlines. But I want to be honest with you about what that phrase does and does not mean, because this is exactly the kind of detail most channels skip. Temperature and heat are not the same thing. Temperature measures how fast individual particles are moving. Heat is what you get when enough of those particles hit you. And out there, the plasma is so unimaginably sparse, a handful of particles in a volume of space bigger than a room, that a spacecraft passing through it does not burn. Voyager 1 crossed it, and its instruments barely registered a thermal load. So no, it is not a wall of flame you could see. But that makes it more interesting, not less. Because what those numbers actually describe is a boundary where particles are being accelerated to extraordinary energies. Something at the edge of our solar system is doing work on matter. Energy is being deposited there, violently, and nobody predicted the scale of it. Scientists thought they had a clean picture of what happens at that edge, until the magnetic data came back. One of the oldest predictions about heliopause crossing was about magnetism. Inside the bubble, the sun's magnetic field, dragged outward by the solar wind, wound into a spiral by the sun's rotation. Outside, the galaxy's own magnetic field, a completely independent system generated by processes far larger than our star. Two fields, two origins, two directions. Cross the boundary and the compass needle should swing. Voyager 1 crossed the boundary. The needle barely moved. The direction of the magnetic field on the outside turned out to be far more closely aligned with the field on the inside than theory had anticipated. A result that genuinely surprised the mission team, and one that scientists have been working to explain ever since. And there is more. At the boundary, the sun's field lines pile up and compress against the interstellar field. In that compressed zone, field lines from different sources can break and reconnect, a process called magnetic reconnection, which releases energy every time it happens. Sit with what that implies. Our solar system and the galaxy around it are not two sealed rooms with a wall between them. At the edge of everything we call home, there's a zone where energy is exchanged, where our star's magnetic influence and the galaxy's magnetic influence are tangled together. We are not in a sealed bubble. We are in a leaky one. Now here is where this stops being abstract. That bubble is not just a line on a diagram. It is a shield. The heliosphere deflects a large fraction of the galactic cosmic rays streaming in from distant exploded stars, high-energy particles capable of damaging DNA, degrading electronics, and stripping at atmospheres over long timescales. Life on this planet has developed underneath that shield, plus Earth's own magnetosphere and atmosphere, for its entire history. We have always assumed that shields are stable and roughly predictable. Voyager 1 is telling us the environment pressing on it from the outside is more turbulent, more structured, and more energetic than the models accounted for. Now, I want to be extremely careful here, and this is where I part ways with the more dramatic versions of this story. Nobody has shown that the shield is failing. There is no evidence of imminent danger. Nothing about this means anything bad is going to happen to you or to anyone this century. What it means is narrower and, in a way, more unsettling. Our confidence was built on models we had never once tested from the inside. The first time we tested them, they came back incomplete. And our solar system does not sit still. Over hundreds of thousands and millions of years, the sun carries us through different regions of the galaxy. Denser clouds of gas, thinner ones. Some researchers have proposed that passing through denser regions could compress the heliosphere significantly, and have raised the possibility that such events could have left traces in Earth's geological record. That is an active area of research. It is not settled. No one can say for certain. But the fact that we now have to ask, and the fact that the only instrument capable of helping us answer it is running out of power, that is the real story here. And in 2023, we very nearly lost that instrument entirely. In late 2023, Voyager 1 started sending gibberish. The carrier signal was still there. The spacecraft was alive, powered, pointed at Earth, transmitting. But the data inside the transmission was corrupted. A repeating pattern of nonsense, unreadable. The team at NASA's Jet Propulsion Laboratory had been reading this spacecraft's output since 1977. Some of them had spent their entire careers on it, and for 5 months they could not decode a single meaningful line. When they finally traced it, the cause was almost absurdly small. A single chip in the flight data system had failed after decades of cosmic ray exposure, a fraction of an inch of 1970s silicon. And the section of code stored on it happened to be the code responsible for packaging science data for transmission. No alarm, no warning. It had simply worn out. Now consider the repair problem. The broken component was 15 billion miles away, unreachable, unrepairable. The only tool available was radio, and radio takes roughly 22 hours to get there and another 22 hours to come back. 44 hours minimum for one question and one answer. Picture that engineering loop from inside the room. You examine a fragment of corrupted data. You form a theory. You write a test. You transmit it. You wait almost a full day. You receive a response. It's slightly different from what you predicted. You revise. You transmit again. You wait again. For months. And every single command carries the knowledge that one mistake, one wrong instruction sent across 15 billion miles to a machine with no manual override and no recovery mission, ends the mission permanently. They solved it anyway. They determined the corrupted memory could not be repaired, but it could be relocated. So they split the affected code into pieces, moved each piece to a working section of memory, individually adjusted each one to function correctly from its new address, and stitched the whole thing back together. Remote brain surgery through a 44-hour delay on a machine built before the personal computer. In 2024, Voyager 1 came back online and resumed sending clean science data. And the first thing it sent back? The hum. Still there. Still unexplained. Which brings us to right now, 2026, and a number that decides everything. Voyager 1's power comes from 3 radioisotope thermoelectric generators, sealed containers of plutonium-238 that convert decay heat into electricity. At launch, they produced roughly 470 watts. They lose about 4 watts every single year. Not from fuel alone. The thermocouples that convert heat into electricity also degrade with age. Nearly 49 years in, the margin is razor thin. So thin that on February 27th of this year, during a routine planned roll maneuver, the spacecraft's power levels dropped unexpectedly. Every year the team faces the same brutal arithmetic. What do we turn off? They have been making those calls for decades. Cameras, 1990. Plasma Science Instrument, 2007. Ultraviolet Spectrometer, 2016. Cosmic Ray Subsystem, February 2025. And on April 17th, 2026, engineers at JPL sent the command to shut down the low-energy charged particles experiment. That instrument had been running almost continuously since 1977. 49 years of nearly unbroken operation. It measured the structure of the space between stars. Exactly the environment this entire video has been about. Off. Voyager 1 now has 2 working science instruments left, out of 10. The magnetometer, which measures magnetic fields, and the plasma wave subsystem, the one hearing the hum. 2 instruments, and each of these shutdowns is permanent in practice. There is no way to unask a question you turned the instrument off for. Each shutdown buys roughly a year of margin. Somewhere in the early 2030s, the arithmetic runs out entirely. But here's the part almost nobody outside the mission team is talking about. They have not accepted it. Engineers at JPL are working on a procedure they nicknamed internally, informally, the Big Bang. It is not an explosion. It is a coordinated swap, turning off a whole group of powered devices at once and replacing them with lower power alternatives, all in a single operation to keep the spacecraft warm enough to keep doing science without burning power it no longer has. The risk is real. Changing how power flows through a 49-year-old spacecraft with no manual override across a 22-hour delay is not something you get to undo. So they are doing it the careful way. They are testing it on Voyager 2 first. Slightly more power margin, slightly closer to Earth, slightly less catastrophic if it goes wrong. Those tests were scheduled for May and June 2026. If they succeed, the same procedure gets attempted on Voyager 1. no earlier than July, which is right now. And here's the detail that made me want to make this video. NASA has said that if the Big Bang works as hoped, there is a possibility that the instrument they just switched off in April, the low energy charged particles experiment, could be turned back on. Not a promise. Nobody at JPL is promising anything. But nearly 50 years of history says something specific about this spacecraft. Every single time anyone has assumed Voyager 1 was finished, they have been wrong. But this raises one more question. Because there is a date already locked into the calendar, and it arrives whether the Big Bang works or not. November 18th, 2026, 2:16 and 7 seconds in the morning, Pacific Standard Time. At that moment, Voyager 1 will be 16,094 by 199,096 miles from Earth. NASA calculated it at second and mile. That number is not arbitrary. It is exactly the distance light travels in 24 hours, one light day. At that instant, Voyager 1 becomes the first object ever built by human hands to sit one full day of light away from the planet that made it. Send a command Monday morning, it arrives Tuesday morning. The reply gets home Wednesday. A 48-hour round trip for a single exchange. No spacecraft has ever crossed that line. Nothing our species has ever built has been that far away. And Voyager 1 will cross it alive, still pointed at us, still transmitting, still listening to a sound we cannot explain. Then it keeps going. Roughly 38,000 miles per hour, adding another 38,000 miles of distance every hour forever, because there is nothing out there to slow it down. No air, no friction, no gravity strong enough to matter. So let me close the loop I opened at the start. The hum is still unexplained. 2 candidate mechanisms, no consensus. And the only instrument in existence capable of gathering more evidence is running on a power supply that drops 4 watts a year and has 2 instruments left. When it stops, that is not a pause. There's no backup. There is no second interstellar probe waiting in the wings. If a replacement mission were funded and launched today, it would not reach the heliopause for roughly 25 years. Which means when Voyager 1 goes silent, sometime in the 2030s, the question it raised stays open. The map it started drawing stops being updated. And the only real-time window our civilization has ever opened onto the space between stars closes and stays closed for a generation. Somewhere in the early 2030s, the last instrument will drop below its minimum power threshold. The final transmission will begin a journey home lasting more than a full day. It will arrive, it will be recorded, and then nothing after it. But the spacecraft does not stop. Bolted to its frame is a gold-plated copper disc. Greetings in 55 languages, the sound of rain, of surf, of a human laugh, 90 minutes of music from across our cultures, and a map drawn from the positions of pulsars showing exactly where in the galaxy we live. Carl Sagan, who helped assemble it, called it a message in a bottle cast into the cosmic ocean. That disk will still be traveling when the sun has swollen into a red giant. It will still be traveling after every city, every archive, every stone we ever carved our names into has been erased. The most permanent object our civilization has ever created is riding on a machine that runs on less electricity than the bulb above your bathroom mirror. Here's what I actually want you to take from this. We have built things larger than Voyager, more powerful, vastly more expensive, more technologically sophisticated by every measure. None of them have told us what Voyager 1 is telling us right now, because none of them had the one thing Voyager had. None of them kept going long enough to actually get there. There are questions about the universe that cannot be answered from a telescope on a mountain, or a satellite in orbit, or a rover on Mars. They can only be answered from inside. We have exactly one machine inside. It is 48 years old. It is dying. It is listening to something we can't explain. And as long as it is still transmitting, somebody should be paying attention. If this one got to you, subscribe and turn on the bell, because the next chapter of this story lands in November, and I intend to cover it the day it happens. And if you want to understand what actually sits on the other side of that boundary, what the galaxy is doing to our solar system on timescales we don't normally think about, then watch this one next, because there's a version of that story where the shield gets thinner, and it has happened before. Tell me in the comments. If you could send one more instrument out there, what would you want it to measure? Thanks for reading.